Something about. All right, so for example number 1, we're going to investigate continuity. Now, we talked about continuity last year in pre-calc. We're going to revisit it because it's important for calculus applications. So for example number 1, it says investigating continuity. So it says find the points at which the function f is continuous. All right. And we want to, and then figure out when it's discontinuous. So a general rule of thumb is if I go to draw the graph and I have to lift the pencil off of the paper, that's a point of discontinuity. So as we look at this, okay, I'm going to go across from here to here to draw the graph, but now I have to lift my pencil off of the paper to draw this second line. Now that's called a jump discontinuity when x equals 1. Here though, when I get to 2, there is an open circle, which means that my function is not defined right at that particular point. And if you look above, there's a circle. So in order to fill in the circle there, guess what? I have to lift the pencil off of my paper. So again, there's another point of discontinuity at x equals 2. Okay? Now, all that limit derivative stuff that we're talking about really depends upon continuity and stuff like that, because the formal proofs, we have to make certain assumptions about the behavior of the graph. So, graphically speaking, to find something that's continuous or discontinuous, you're going to look for discontinuities. Jump discontinuities are where the function literally jumps from one location to another. A removable discontinuity usually has an open circle that you would plug in the circle somewhere else. So we have an open circle here, but I can define the function as a function because I have a closed circle up here. But again, anytime you have to lift the pencil off of the paper, usually it's discontinuous at that point. Okay? Anybody have any questions? Now what they want us to do though is they want us to look at the limits of that function. So here's the thing. The limits of the function, for example, at x equals 0, we have a limit, but it's a one-sided limit. Okay? And at 4, we have a limit, but it's a one-sided limit. And so what they're saying is, let me zoom in a little bit. What they're saying is that at 0 less than c less than 4 and c cannot equal 1, 2, then the limit of f of x exists. But it doesn't exist when the function is not continuous. So remember, we're ramping up to derivatives. Derivatives are based on that formal definition of a derivative, f of x plus h minus f of x all over h as h approaches infinity. Well, if you can't take the limit because it's not continuous, then you can't take a derivative of a discontinuous function. Now that doesn't mean that you can't observe the behavior. It doesn't mean that you can't do some trickery, some wizardry to make it work. But basically, this function, you're able to take a limit of this function anywhere except for the points of discontinuity, which is 1 and 2. Does that make sense? Okay. Now, a lot of times what we do is we'll find a similar function that's identical to the other function that is continuous over the point, and we go from there. And so let's continue on reading that. Well, it says that the limit doesn't exist at 1. Okay. And it says here at 2 that the limit of the function is 1, but 1 does not equal f of 2. Okay. So the more formal definition of continuity at a point, an interior point a function y equals f of x is continuous at an interior point C of its domain so long as we're able to take the limit of f of x as x approaches C, and that'll give us the value f of C. That was our problem here. We had a function and we were able to take a limit based on the graph. However, that's not what the function was defined at. We're talking about this right here, so let's slide back and look at this graph. As x approaches 2, we can take a limit because it looks like it's approaching 1 from the left-hand side. It looks like it's approaching 1 from the right-hand side. However, it's defined at 2. So we say that it's discontinuous because we could take the limit, which is equal to 1. However, 1 is not what the function is defined at. F of 2 is 2, not 1. Okay? And so these points are not in the domain 0 and 4 because they're the end boundaries. And so as long as when we take the limit of f of x as x approaches C and it's defined at that same value, then we consider the function to be continuous at an interior point. Now a function could be continuous at the end points, left or right end points, so long as the same thing applies. However, we take the limit from one side or the other and they're still defined. Okay? Respectively. So, for example, this is defined at 1. So if I look at the function and I approach 0 from the left-hand side, it's defined as 1. The limit is, and the function itself is defined as 1. So my limit equals what it's defined at. F of 0 equals 1. My limit of f of x as x approaches 0 is 1. 1 equals 1, therefore it's continuous. It's a one-hand-sided limit, but it's continuous. It's an endpoint continuous, right? It's a continuous at the left endpoint. And then if we look at the right endpoint, we do the same thing by looking at the graph. As I approach 4, it is approaching, the y value is approaching 1. As x approaches 4, y approaches 1. By the way, f of 4 is 1. Since 1 equals 1, we consider the function to be continuous at the end of the domain. Okay. All right. That's it for example number 1. Do you guys have any questions?